Tesla is the world's largest purchaser of lithium-ion batteries. This means that those who are creating and researching battery technology come to Tesla first with their discoveries. Tesla has previously stated that they frequently receive battery samples and that they keep track of hundreds of battery research programs to which they allocate points based on their potential. These experts are reaching out to Tesla because they believe they have the best possibility of bringing new battery advances to market, as well as the most willingness to do so. It needs to be noted early on that taking any battery breakthrough from a research paper in the lab to a viable commercial application at scale has historically taken 10 to 20 years, and moving forward it may still take 5 to 10 years. The researchers work on concepts and develop strategies and architectures to understand how the cells work, but the development, scaling and testing is done by the industry. Someone like Tesla or Panasonic would have to license the tech from the lab, and then invest heavily to develop production methods at scale that don't yet exist on technology that's not completely understood. Hello, and welcome to Inferno Rocket, where we'll keep you up to date on all things Tesla, SpaceX, and Elon Musk. Let's go over the basic operation of today's lithium-ion battery to make sure everyone understands the research in this video. They're made up of 4 major parts: 2 electrodes, 1 anode, which is typically but not always negative, and 1 cathode, which is made of graphite or silicon. The other electrode is a cathode, which is usually positive and is made up of a variety of cell chemistry. The anode will be referred to as the negative electrode, and the cathode will be referred to as the positive electrode from now on. Between these electrodes is a separator, which is a thin material that prevents physical contact between the electrodes, allowing the electrolyte to be thin as well, making batteries smaller, lighter, and better. When a battery overheats, the gaps in the separator melt shut, shutting down reactions in the battery and preventing fires and explosions. All of these ingredients are found in a liquid electrolyte, with lithium salt making up part of the electrolyte and a solvent in which lithium salt dissolves. These liquids have the potential to be combustible, more on that later. Electrodes act like sponges, absorbing lithium ions and electrons, which combine to form actual lithium inside the electrode. A discharged battery has most of the lithium trapped in the positive electrode sponge, so charging a lithium-ion battery is all about moving the lithium ions and electrons from the positive electrode to the negative electrode. The separator prevents electrons from flowing through the battery and forces them to move around it in order to power the load. Your EV motor, in this scenario. On the other hand, lithium ions flow through the electrolyte and separator. The electrolyte substance's main feature is that it must allow lithium ions to travel freely back and forth between the electrodes while preventing electrons from passing through. Furthermore, the electrolyte substance must be chemically favorable to the electrodes in order for them to maintain their stability. When a load is given to the battery, such as driving a car, the trapped lithium becomes unstable because the electrons now have somewhere to go, splitting the lithium ions and electrons. With the electrons making their way to the load as the discharge occurs, the lithium ions travel back to the positive electrode through the electrolyte in the separator, where they rejoin the electrons that just passed through the load, creating lithium. When a battery is being charged, electrons and latium ions are drawn from the positive electrode to the negative electrode. All of these components are made extremely thin, down to fractions of a millimeter, allowing the materials to be laid flat and then coiled up into a much smaller space. In Tesla's case, they're linked together into modules and battery packs after being formed into a cylindrical cell the size of a double A battery. The battery community largely agrees that lithium-ion cells are nearing their theoretical maximum capacity, although how close they are to that theoretical maximum capacity is debatable. Furthermore, the liquid electrolytes utilized in today's batteries are flammable, making them inherently more dangerous and fire-prone. Bend rates, which are lithium metal crystals that trigger a variety of unfavorable reactions in the cell, can arise while charging at greater rates. At worst, this could result in a short circuit, fire, or explosion. When you combine the safety concerns with other restrictions such as energy density and cycling efficiency, it's easy to see why a new battery technology is needed. However, solid state in its most basic form, This new technology would use a solid as the electrolyte, such as glass, ceramics, or sulfides, rather than a liquid. As a result, the term solid state was coined. Solid-state batteries' cathodes are primarily lithium-based, but other variations have been investigated. Lithium-sulfur is one potential material for the cathode. Because of its solubility, sulfur cannot be employed as a cathode in liquid electrolyte applications, resulting in shortened battery life. Because of the type of solid electrolyte utilized, the anodes of solid-state batteries are far more powerful than the cathodes. Because of its high energy density, several academics have hailed a lithium metal anode as a key to a big solid-state breakthrough. Solid-state batteries have been investigated since the 1950s, but they've gotten a lot more attention and money in recent years thanks to the big lithium-ion boom. There's a reason for that. One reason is safety, but there are many others. Solid-state batteries will have a lower form factor. By removing the liquid solvent, the battery's size can be dramatically reduced. They'll lose weight overall and have better energy densities as a result. Without going into too much detail, some of the most cutting-edge solid-state research employs a lithium metal anode, which has the potential to double the energy density of today's lithium-ion batteries on its own. In theory, that would mean going from a 300-mile range Tesla to 600 miles. In commercial settings today, lithium-ion batteries peak at around 250 watt-hours per kilogram. For example, in Tesla's Model 3. Watt-hour per kilogram is just a unit of specific energy used to measure the density of energy in batteries and capacitors. There have been many claims from the solid-state research labs worldwide with numbers between 400 and up to 1,000 watt-hours per kilogram. Anything in this range would allow massively extended ranges, or smaller, cheaper and lighter battery packs. Additionally, solid-state batteries can result in much lower cost because they minimize the safety features required and remove the need for a thermal management system, of which Tesla currently has the best in the industry. This all sounds great and progress is being made, but it's simple to understand from a high level why this is such a technological puzzle. Moving lithium ions through a liquid is much easier than moving them through a solid. By the way, if you like what you're seeing, please subscribe to our channel, where we keep you up to date on all the latest news from Elon Musk, Tesla, SpaceX, and, of course,
Simplify,
Neuralink.
there are many unknowns about this new cell chemistry. The second paper claimed a lifetime of 23,000 cycles, which seemingly increased over time without a clear limit, and an ability to self-charge. Pair this with the huge energy density claimed in the first paper, and that would indeed be revolutionary if they could be produced at scale for EVs. The size of this if cannot be overstated.
The first
Many
research
researchers
paper,
have since
titled
moved on from this work,
for a
but
safe
because of John
rechargeable battery, was accepted in December 2016. They announced the development of a low-cost, all-solid-state rechargeable lithium or sodium battery cell that uses a solid glass electrolyte and promised to operate at lower temperatures. The research stated that dendrite growth would be eliminated, resulting in a new cell that would be easier to build, have cheaper costs, and have considerably higher energy densities of today's lithium-ion batteries at least 3 times. A longer life cycle, and charge and discharge rates that are acceptable. Sodium is less expensive than lithium and is readily available from the oceans, making it a better option than lithium, however it may have less capacity. The Good Enough in Braga team's second publication on the Braga glass, titled, Non-Traditional Safe High-Voltage Rechargeable Batteries with Long Cycle Life, was published in June 2018. It's worth noting that the filtering process for published work has degraded as a result of the massive influx of peer-reviewed research publications. The mere publication of a research article does not imply that something revolutionary has been discovered. Many papers are published in order to enhance the field of study and aid future breakthroughs. Both of these publications were received with suspicion by well-researched and well-respected leaders in the battery industry. To put it another way, there are a lot of unknowns regarding this new cell chemistry. The second report claimed a lifetime of 23,000 cycles, which grew over time without seeming to reach a limit. As well as the capacity to self-charge if they could be mass-produced at scale for electric vehicles. This, along with the large energy density cleaned in the first study, would be revolutionary. It is impossible to overestimate the magnitude of this. Many scholars have now moved on from this work, but many people in the general public and investors implicitly accept John Goodenough's strong and daring reputation, which he completely deserves, more than what's really presented in the paper. It should be mentioned that in the 2018 publication, half a drop of liquid electrolyte is used to make the electrode and electrolyte stay together. When asked about solid-state batteries on an investor conference call about a year after the first study was published, Elon and JB had strong emotions regarding the new technology. "We plan to license the technology to many manufacturers. We want to avoid an exclusive license. We're establishing a patent portfolio that I hope will prove profitable," John Goodenough said in a 2017 interview. "We will not grant you an exclusive license. Manufacturing a commercial battery cell will take a competent battery business roughly 2 years of research, but we have over 50 companies interested in testing our results." Unquote. Anyone can and will have access to this technology, and while Tesla and Panasonic have the best chance of commercializing it, everyone else should be able to catch up rapidly. This might actually erode Tesla's current competitive advantage. Almost every other legacy OEM has put a significant amount of money into solid-state startups. Ford, BMW, and Hyundai have invested in a solid-state battery startup called Solid Power, evidently waiting for a breakthrough. Honda, in collaboration with Caltech and NASA's Jet Propulsion Laboratory, claims to have developed an entirely new fluoride-ion battery with a 10-fold increase in energy density. However, it should be emphasized that a liquid electrolyte is still used. In 2019, the U.S. Department of Energy awarded GM a $2 million grant for the development of solid-state batteries. $1 million will be used to explore hot pressing of reinforced solid-state batteries with sulfide glass as the electrolyte, and the other $1 million will be used to better understand solid-state battery interactions. GM and LG Chem are collaborating on a $2.3 billion joint venture to mass-produce battery cells. However, these are likely to be lithium-ion batteries rather than solid-state batteries. The Chevy Volts batteries are made by LG Chem. Quantum Skate, one of the major US-based solid-state battery startups, received a $100 million investment from Volkswagen. They've stated that their goal is to set up a solid-state cell production line by 2025, but they don't expect them to be mass-produced until closer to 2030. Toyota is planning to show off a solid-state battery vehicle at the 2020 Tokyo Olympics, but CTO Shigeki Teraji said a production vehicle won't be ready until the mid-2020s. There are also a number of side agreements in place. Toyota, Nissan, and Honda have partnered with Panasonic to develop a solid-state battery with a range of 340 miles by 2025 and 500 miles by 2030. Panasonic has stated that solid-state lithium batteries will not be economically feasible for another 10 years because there is no proper mass production technique for these batteries, and if any business that knows this issue, it is Panasonic. Most legacy automakers are hoping for solid-state battery technology to become commercially feasible between 2025 and 2030, as evidenced by the industry as a whole. This brings us back to Tesla, where Maxwell is bringing a dry battery electrode coating technique, or DBE coating technology, to the table. This DBE technology is compatible with present and future battery chemistries, as recently revealed publicly. They were also working on ultra-capacitors, commonly known as supercapacitors, but Elon has recently stated that these are superfluous and that we would not move forward with supercapacitors until something changes. Unlike conventional wet-coated electrodes, DVE Tech manufactures a thick electrode that enables for higher energy density cells and faster discharge rates. The scalability of this manufacturing technique has previously been proved by Maxwell. Solvent toxicity, electrode reactivity, and extended mixing and oven drying times are all disadvantages of traditional wet coating methods. Maxwell's innovative solvent-free coating technology tackles these problems while also lowering manufacturing costs and improving performance, allowing for novel battery chemistry development. Reduced solvent usage equals substantially greater production rates, which necessitates a much smaller and less expensive manufacturing footprint. The cohesion and adhesion qualities of electrodes, which are derived from the dry coating method, are superior in the presence of electrolytes at high temperatures, in addition to manufacturing flexibility. The dry coating electrode technique is ecologically safe, and it can be easily deployed with a significantly smaller startup capital cost, because it eliminates the use of any solvents, as well as the accompanying coating and drying complexity that come with wet coating technology. As a result, dry coating electrode production is both cost-effective and ethically responsible. Maxwell's dry coating technology consists of 3 steps: dry powder mixing, powder to film formation, and film to current collector lamination, all of which are completed in a solvent-free environment. Maxwell has been working on this DBE material since 2011, indicating that it is likely ready for commercialization. They don't create batteries or deal with cell chemistry. Instead, they make automated pump systems that have been used to feed liquid electrolytes into batteries, a procedure that may theoretically work well with a Maxwell DBE. The new Maxwell DBE technology is not the same as a solid-state battery because the DBE manufacturing method still produces a battery with a liquid electrolyte. Tesla may now inject a new electrolyte composition into their next-generation batteries using high-pressure, world-renowned pump filling technologies. This brings us to Jeff Dahn and his associates. He and his colleagues have conducted extensive testing with a variety of improved lithium-ion electrolyte chemistry and electrode compositions. They made this data public, but Tesla had a patent published in December of 2019 that appeared to result from their research. At Battery Investor Day, Tesla may combine the DBE from Maxwell, the pump filling from Hibar, and a new battery chemistry from Dahn and Company. If the Maxwell technology can boost Tesla's watt-hours per kilogram from 250 to 300, which has already been proved, that's a 25% gain. Maxwell has also stated that they've identified a way to achieve 500 watt-hours per kilogram, which, as you may recall, is higher than some projections for future solid-state batteries. If it can also extend battery life by 2 times and reduce production costs by 10 to 20%, and you add synergies from high bar efficiencies and a new chemistry from Dahn and Company to these figures, it may be argued that Tesla will not require a solid-state battery in the foreseeable future. However, Maxwell claims that their DBE technology will enable the construction of solid-state batteries in the future. The new battery type will include not only a thorough examination of cell chemistry, but also of module and pack architecture, as well as a manufacturing plane with a clear path to a terawatt-hour of annual production. They'll almost certainly discuss their latest battery pack patent, in which they've simplified the multiple battery module system into a single module, resulting in a more efficient system. Who's eager to see this new battery technology be released into new cars? Let us know your thoughts on the topic in the comments section below. A quick reminder to subscribe to our channel. There's a link down below for more Tesla news and conjecture. If you want to learn more about Tesla, SpaceX, and Elon Musk, we have 2 more video alternatives for you to watch on the screen. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more weekly news like this.